When an object moves through a gas, it experiences a force in the opposite direction of its motion. And this force is called the drag force, and it's governed by this equation here. So in this video, I want to explain how this equation works and what is the underlying principles behind it. But before doing that, let's get to some basics. When an object moves in a straight line, we can parameterize the motion of this object by some function x of t. And so where the object appears along the line is just x of t, and so its position is simply this function x of t. The velocity of the object is going to be the first derivative, and therefore the momentum, which is the mass times the velocity, will be the mass times the first derivative. An important concept here is force, which is mass times acceleration, and as it turns out, this is exactly the derivative of the momentum. Okay, so here we have a very simple picture which is going to help us think about what drag really is and what's the underlying mechanism which causes drag. And of course this picture is not the full reality, no picture is, but it does give us a very good intuition which will guide the mathematics that we'll do later. So here we have our object, and it's imagined to be moving through this gas, and after it moves it collides with some particles which are given here. Now what is a gas? Well, a gas is nothing other than just some freely floating particles. So these particles are just moving in various directions and they do not interact with each other in any way. That's the assumption of the ideal gas model. In reality, of course, they do, and there are models which incorporate this into the model. So when this object moves through the gas, it's going to collide with these particles and actually exchange some momentum. So it's going to speed up the particles, and that's what's happened here. Now, because momentum is conserved, it must mean that this object has lost some momentum. And that's really the key detail that's going to tell us what drag is. So as it's moving through the gas, it will lose momentum because it's exchanging some momentum to these particles here. Okay, so let's take a closer look here and try and get a bit more mathematical with this picture. Okay, so let's try to quantify the momentum exchange from this object to the gas in a certain very small interval of time, dt. So we have to think about this as all happening in some interval of time, because the longer the object moves for, the more momentum will be exchanged. Okay, so in this interval of time, we're going to call dp, that is going to be the change in momentum of our object in the interval dt. Then this is going to be proportional to two things: the mass, the amount of mass that the object collides with, and the velocity of our object. Where it gets interesting is that the amount of mass that the object will collide with is itself going to be proportional to several factors. Firstly, the cross-sectional area is going to be important. The bigger this area is, the more particles it's going to collide with, and so this is one of the reasons for this proportionality here. So the amount of mass the object will collide with is definitely going to be proportional to this area. Also, another factor which is important is the density. Of course, the more particles per unit volume, in other words, the bigger the density, the more mass that the object is going to collide with. And so that explains why the density is important. The next thing is the distance that the object will travel in a certain interval of time, which is this interval dt. And so if the object moves only, let's say, from here to here, well, then it's only going to interact with this particle, that one, that one, that one, maybe this one, that one, maybe that one, and that one. But if it had to move from here to, let's say, here, well, then it's going to collide with all of these. And so how far the object will move in this interval dt is going to be an important factor. And in fact, we can say exactly what that is. of course, that's going to be just the velocity of the object times dt. Velocity is nothing other than distance over time. So that gives us all the relevant factors here. And so we can say that the mass, the amount of mass that this object collides with is proportional to the cross-sectional area, as we said, times the density of the gas, times v dt. Okay. And we can put these two things together. So the momentum exchange here, if we have to try and say what is the momentum exchange proportional to, well, we said the amount of mass that is collided with and the velocity of the object. So here's the amount of mass. And here's the velocity of the object. And so this gives us that, just reorganizing the equation, this gives us this. And why it was done this way is that because we have this proportionality, we know that the real momentum exchange is nothing other than a constant times this quantity here. And then we get something very interesting here, and that's that the change in momentum over time is equal to this Ka sigma v squared. And what is change in momentum over time? Well, we saw earlier, this is nothing other than the force due to drag. Momentum over time is force. And so that's how we can get the drag equation right here. So let's finish this video off with a practical kind of a problem. So let's imagine that this object is moving through our gas and there's no other forces acting on the object other than the drag force. And what we're interested in determining is what is the shape of this function? What explicitly is this function going to equal? Well, we can determine that because we have the drag equation, so that the only force on our object is the force due to drag. And so that's going to be equal to the constant k, which we don't know exactly what it is, but in practical situations it's determined for a given object with a given shape here. And so k times a times sigma times v squared. And here we can just realize what is force. Well, it's mass times acceleration. And this is equal to k a sigma v squared. And then acceleration here is nothing other than the first derivative of velocity. And so we have this. Now, this equation, it's a differential equation, and moreover, it can be transformed into a special kind of differential equation, namely a Bernoulli equation. And all you have to do is divide both sides by m. So you have dv dt is equal to k a sigma over m v squared. And this will turn out to be a Bernoulli equation where the n is equal to 2. The power on the right-hand side is equal to 2. And so you can see my video on the Bernoulli equation, and if you're interested in solving it, you can solve it for the specific differential equation. And even if you wanted to incorporate other forces, so imagine you had an object which was falling. So imagine you have this object here, and it's going to be falling in a gas, or let's say the air, and it has a specific the specific constant k in the situation, which we don't need to know exactly. But if you wanted to determine the motion of that object over time, you could also do that. So another question you may ask is, well, what is the terminal velocity? There's a couple of ways of figuring out what that is, but it's interesting to just look at these things for yourself. Okay, thank you.